Everyone, I think we can start. I see a lot of rectangles in front of my screen, which is a good thing. I hope you are ready for a new session, a new installment of the YRTG meetings. Today, before we start, I would like to just say a couple of points. So the first one is that we have been contacted by people that are interested in joining from outside of the European time zones. So we will probably have to meet and discuss the implementation of the new time schedule for these meetings. So that's underway. I just wanted to let you guys know. And then second, let me remind you about the structure of these meetings. We will have a talk for 45 minutes, and then we'll follow this with 45 more minutes of discussion, which can be indefinitely extended if people are so inclined. With this out of the way, it is our pleasure and my particular and personal honor to introduce Maximilian Ruep from the University of York. Maximilian did his master's degree in Munich at the LMU and at the TUM on algebraic quantum field theory, and in particular, if I recall, on the self-adjointness of Noether charges. And he's now working for his PhD in York, still continuing the line of research associated with algebraic quantum field theory. I would say that Maximilian's interests are generically foundational questions of physics, and particularly those that can be easily or nicely tackled by mathematical methods. Today, Max will tell us about measurements or constraints on measurements from locality in general spacetimes in quantum field theory. So please, Max, the floor is yours. You have our attention.
Thank you very much. Let me share the screen in a second. Yes. Good, perfect. Thank you very much for the nice introduction. And it's a pleasure to be here and talk about my work. So today I'd like to talk about causality in quantum field theory on a fixed background, which is really kind of a report on results of joint work together with my PhD supervisors here in York, Chris Fewster and Henning Bostelmann. So let's get started. I want to start with a disclaimer, kind of a menu of today's talk. What will there be today? There will be fixed non-dynamical backgrounds with fixed causal structure. So don't expect something else. There will be also external observers, external entities, external agents. And finally, we will talk about, well, causality in quantum theories on these fixed backgrounds, where in some sense the notion of causality comes from this fixed non-dynamical background. And let me stress again, what we will not have today, we will not have a dynamical background. We will not get rid of any external agents. We will not have a kind of, a theory of everything in this sense. There will always be some external entities that are not described by the theory. Okay, and then without further ado, let me get started with some basics. And as I said, my background is in algebraic quantum field theory. So in some sense, it is no big surprise that I would like to take an approach to a characterization of a system following the algebraic approach to physics. And there in particular, a system, S here, is characterized by its observables. So by all the observable content of the system itself, all the possible configurations and the things that you could observe. Now, it's actually very nice in the algebraic approach that after some idealization, you can argue that observables should be regarded as the self-adjoint elements of a unital star algebra. So that means that if you have two observables, right, A and B in S, then you should be able to form linear combinations with complex numbers. And you should, moreover, also be able to form products, okay? And then this multiplication, to be able to form products, should distribute over the addition such that this whole thing then turns into an algebra. And moreover, what we also want, what's also convenient, is to have a star operation here. which I usually denote by this little dagger here. So a dagger, right? This is the star operation. And yeah, so a structure that has all of these, algebraic relations, algebraic addition, multiplication, and the star operation is called a star algebra. And if we also have a unit, an identity operator with respect to the multiplication, then this forms a unital star algebra. If you want to throw in some more structure, you can easily do that. What might be convenient is to equip this whole thing with a norm, a special norm, then you get a C-star algebra. Or if you even want to be more special, you can also go over to von Neumann algebras. And as always, if you throw in more structure, you can make more interesting statements in the end. But for our purpose, it's really, we can make do with a unital star algebra, at least at the beginning. Okay. But then again, observables on their own are not so interesting, really, because we also want to talk about results of actual measurements, actual observations. And for that, we need to, in some sense, map observables to something that we can observe. And in this probabilistic approach that we have in quantum theory in particular, we need an additional input that are states that correspond in some sense to preparations of the system, and states that map observables to expectation values, right? So you have an abstract observable, and then you want the state, and then the image of this abstract observable in a state should give an expectation value. And in order for a state to be able to do that, a state omega on S should be a linear map that fulfills the following. It should be unital, so it should map the identity to 1, and it should be positive. So for every A, an element A dagger A, this is a positive element, should be bigger or equal than 0. So it should map positive operators to, well, non-negative numbers. So you might wonder where these two criteria come from. It has something to do with maintaining this probability interpretation in quantum theory, right? So maybe let me quickly say something here. So suppose you have some observable P, right? And you can think of P as a projector. Then you have, of course, also the identity minus P, as in some sense, the opposite of what you want to observe. So P could, for instance, be an observable associated to a click in the lab, observing a photon, something like that. And 1 minus P would then be the opposite, not observing the photon, the detector doesn't click or something like that. And the probability that the detector clicks is then omega of P. The probability that the detector does not click is this. If you add them, they should be 1, of course. And in particular, for those to be probabilities, they should be bigger or equal than 0. Okay. So just to give you a very, basically the simple motivation for these maybe rather abstract definitions if you're not used to this algebraic approach. And also to make it easier, I thought I give you an example. I hope I don't bore you with this. You can think of a two-level system, a qubit, in quantum mechanics, right? So what is a qubit? What are the observables of a qubit, or what is the algebra associated to a qubit? Those are the 2x2 matrices with complex entries. And every observable there is given by, well, the Selber joint elements, Hermitian matrices. For instance, you can look at this projector P, and then every state is, in particular for this matrix algebra, is indeed of the form trace over some density matrix against your observable A. And for instance, you can look at this totally mixed state here. I've written the density matrix down, and then indeed you can find that the probability of observing this observable, this projector, this effect P is in this totally mixed state 1/2. Okay, good. So so far so good. So now we've talked about observables and systems in the algebraic approach. Now we come to the next ingredient. I hope you can read this because there is still this zoom bar. The next ingredient are fixed backgrounds. So let me start with what is the purpose of a background? What do we want to get from a background? Yeah. In some sense, I've written down here 4 points that I personally think are interesting coming from a background, or that we utilize often when we have a background. The first one could be, we want to have something like time orientation, okay? And time orientation should be thought of broader, not necessarily as referring to one particular time, but maybe rather to notions like, early and late, past and future. In particular, when you think of scattering experiments, right? You need to have a notion of something comes into the system early, ideally, and something goes out late. So you need to have this notion of early, late. And the next thing that you want to get from a background is you want to have a notion of causality. Something can signal to something else or not. They are in causal contact, they are not. This is also a notion that comes from the background. The third point that I wanted to mention here is that you also want to have this notion of a subsystem. So for instance, you have a bigger system and you want to constrain yourself to maybe only a part of the system, which should be, a system in its own right. And how you go from the bigger system to the little system, what characterizes this little system, what characterizes the subsystem, this is usually, or might also be, something that you want to take from a notion of a background. So there is this idea that I heard recently in lectures by Rovelli, where basically he stresses the fact that in gravity, so what defines a system is in some sense, locality. It's that you are confined in a space-time region, which is in some sense the same in a QFT, as we will see later. But can also be viewed as more general, this notion of a subsystem. And then finally, you also want to talk about a notion of dynamics, of causal evolution. Maybe not necessarily that something really evolves with time, but rather that, if you know something, then maybe something else is uniquely determined by that, okay? I know this is now very vague, and we will talk about this in more detail a little later, but you can think of instance for an initial value problem or so, if you know your values on the Cauchy surface or something like that, and you evolve your field, for instance, right? Then it suffices to know the values on the Cauchy surface, and everything that comes later is in some sense uniquely determined. In that sense, you have a causal evolution. Good, and if we take these requirements on the background, we could say that, okay, this motivates to think of a background as, an index set, a set of labels in some sense, yeah. And this should come with the following functions and relations. First of all, it would be good if we had something like a cannot signal to relation, this first relation here, yeah. So for two indices A and B, we would like to have something like A cannot signal to B, which expresses in some sense the causality, but also really expresses something like, more or less time orientation, or, really a causal relationship. Coming from this, we have this perp here, which is a causal disjointness relation, which is, immediate from this cannot signal to relation. So A and B should be causally disjoint. Well, if A cannot signal to B and B cannot signal to A, then you would also like to have such a subsystem relation, such that, it could be that some labels, some indices, A, for instance, should be in B. Okay, so you want to have such a partial order on your index set to be able to talk about subsystems. And in this concrete case here, in indices for the background, an index that denotes something that's maybe smaller, contained in some sense already in the bigger index. You might also want to have something like a maximal element, such that every index that you have is in some sense contained in the bigger index. There is an index which all the other indices are contained. And maybe let me stress here that this is maybe not the most general thing you can do, but for our discussion, this will definitely suffice. And finally, giving credit to this notion of dynamics, you might also want to have a function D, okay, that if you feed it one index, you get out another index in this index set, okay? And you can think of heuristically saying that, well, everything that's contained in D of A should already be uniquely determined by A, okay? So if you know A, you know D of A, let's say, and you know everything that's happening in D of A, okay? And I appreciate that these relations might be up to a certain point very abstract, but there is a nice example for such an index set, which is in some sense also probably the motivating example for demanding these requirements, which is given by, M, a globally hyperbolic spacetime, and I should be all open and causally convex subsets. Yeah? So a causally convex subset could, for instance, be given by such a little region here, okay? And if you take as your indices all open and causally convex subsets, you get a perfectly defined index set. Now, what is the cannot signal to relation? Well, A cannot signal to B if and only if A is not in the causal past of B. So let me draw a little nice A here and a little B here, and let me draw the causal past of B, right? So this is J minus of B. And if A is not in the causal past, well, it cannot signal to. And what is then this causal disjointness relation? Well, it means that your space like separated. So A has empty intersection with the causal past or the causal future, right? Good. So maybe a last thing about this Cauchy development, D, which takes the place of this maybe abstract, or here is abstractly defined domain of dependence. The idea is that if, let's say, your region A is so small, yeah, so this is A, then you want that this here, in some sense, so this enveloping diamond, this is called the Cauchy development. You want basically that everything that's happened inside here is completely determined by knowing A, okay? And what is the heuristic picture? You can imagine, well, you know, if you want to know what's happening basically here, it suffices if you go back in time that you know everything that happened here, okay? So it should be uniquely determined. So everything that's in some sense, this enveloping diamond should be uniquely determined. So this is maybe just to give you an understanding about how dynamics can be encoded abstractly here. And I guess I will not go into any too much detail about the notion of dynamics, because we will focus a little more on the notion of causality here. Good. So let me continue, if there are no questions at this point, with putting the notions that we've discussed together. So we had the notion of a system, we have the notion of a background. Now let's just put this together in some sense a very natural way, which gives you immediately the definition of an algebraic quantum field theory. So this is a definition. A theory on I, so this background, right? So the background is viewed of this set of labels, this index set, is a map from an index to unital star subalgebras of S, okay? So such that this first property holds. So we associate to indices, algebras, systems, right? And in particular, we want that the algebra that we associate to the whole system M, right? So this maximal element in the index set is the whole algebra already. Good. And now we want to associate to every other index, right? That's in some sense contained in M. We want to associate subalgebras of S. This is the second property, okay? So if you think that you have some index set, for instance, here N2, and there's a little index set N1 in there, then you want that the algebras are also nested, right? You want that the system that you associate to this little region here should be a subsystem of the system that you associate to the bigger region here, okay? And as you see, it's very instructive to, when you think of this index set, to draw in some sense regions in something like a two-dimensional space-time or so. Good, so this is this second property, which tells you something about subsystems, you know, and how these subsystem relations on the background side should be related to the system side. And the third point is space-like commutativity. You want that if N1 and N2 are causally disjoint regions, yeah, then you want that the algebra that you associate to here and the algebra that you associate to here, they should commute. And finally, you can also encode this notion of dynamics, right? So if you imagine that you have your little region N here, and you have the enveloping diamond, how I call it, this D von N, then the algebra that you associate to this little region is already the full algebra of this whole D of N, okay? So indeed, everything that you could measure, every observable that you could measure in this whole little diamond is already present in this little region N here, which tells you that there is some causal dynamics there. Yeah? You can calculate something from knowing all your observables of your system in this region N. Good, so this is a definition, maybe a few remarks here. If you come more from a quantum information background, then you might be, well, then you might like the Schrödinger picture more than the Heisenberg picture. But in this algebraic approach, let me emphasize that we're working in the Heisenberg picture. And this follows simply from the fact that we associate algebras to the background, okay? So if you think that, that your background, that M is, for instance, the real line, and you associate algebras to little, you know, intervals on the real line, then it's clear that we are in the Heisenberg picture because we associate algebras to this region here, for instance, and algebras to this region here. So in some sense, you know, the observables feel the passing of time here in this one-dimensional, you know, or 0 + 1-dimensional case of a real line in particular, okay? So the observables have this dynamics encoded just by associating observables to parts of the background, and the state itself is fixed, okay? So the state is global in some sense, and the dynamics is encoded in the observables. Good. So then another remark that might help you to understand what we really mean by an observable in this sense, and something that helped me in particular understand this, is that the color of a chameleon is not a good observable. Why? Well, because a chameleon can change its color, you know? So a good observable is the color of a chameleon at time t, okay? Or, yeah, so because this is a good observable, right? Good. And of course, the dynamics is encoded in this last property. I stress this here explicitly again. And what this means for the color of the chameleon is that, you know, if you observe the color of the chameleon, let's say at time t here, right? And at some other time t prime, you know, all the properties of the chameleon, you know, you are able to calculate in some sense the color of the chameleon at time t. Yeah. Okay, so this is just probably an easy fact, but I still wanted to stress it. But again, we don't want to talk about the dynamics, not necessarily, at least we want to focus on this third property up there, here, which is the spacelike commutativity. And in some sense, intuitively, the idea is that when you take your conventional quantum field theory course, you learn about causality and you say, you know, fields at spacelike separation commute. So causality is restored, you know, the field is causal. But I would really like to investigate this a little more and discuss with you how, in some sense, the spacelike commutativity really encodes causality, or how much of causality is already encoded in our AQFT on a fixed background once we have this third axiom here, the spacelike commutativity. Good. And for that, I go over to the next point, if there are no questions. Perfect. Then I would like to talk a bit about the early ideas of causality. So if you read this, the seminal paper of Haag and Kastler, then you see that the idea of causality that they had was the following. Suppose you have spacelike separated subsystems. Yeah, so you have an N1 here and some spacelike separated N2 here. The idea that they had was the following, you know, associated to this S1 is an algebra S of N1, N2 is S of N2, And the idea is that if you're an observer and you have control of your laboratory in N1, for instance, right, then you should be able to prepare your observables, your system, in any possible state that you want. Okay, so you have your system in N1 in a state omega-1. And also the same, of course, in N2, because they're space-like separated. You should be able to prepare them independently from each other. But what does that mean? You have to appreciate the fact that this N1 and this N2 are actually subalgebras of a bigger algebra. Yeah? So in particular, you want that for those states, omega-1, 2 on Sn1, 2, there is a state omega on all of S, such that when you restrict it to either of the subsystems, you get either of the states. Okay, so this really tells you that you should be able to prepare, you know, space-like separated systems independently from one another. This was the actual motivation for introducing this space-like, well, the space-like commutativity, or at least what Hagen-Castler thought was that this should at least help in showing this kind of causality. And indeed, as was later shown, if you fulfill space-like commutativity and some additional assumptions of a more technical nature, probably you might say, then indeed this notion of causality holds. And moreover, it's also very nice that this notion of causality immediately generalizes to n mutually space-like separated NJs. Yeah? So if you don't just have two observers in the world, but like n observers space-like separated, then this notion of causality easily generalizes. Okay, so good. This is the early idea of causality. This is the first notion that we encountered. And it truly makes sense, because you really should be able to prepare your systems independently from one another if you're space-like separated. But is this really what you think of when you think of causality? I would like to discuss another idea this year, which touches on a slightly different aspect, which is the following: that for every N1 and N3 that are space-like separated, so let's say you have your little N1 here and your little N3 here, right? And they are space-like separated. The idea should in some sense be that any local operation that you perform in N1, anything that you do in N1 to your system, does not affect what the person in N3 observes, sees, does, whatever. It doesn't influence N3, no matter what happens, okay? So no matter what happens to the rest of the system, no matter what anyone else outside my lab does, no matter what anyone does, if I do something in N1, then N3 shouldn't know, yeah? Or the region N3 should not know. And here I have this little, this little caveat. It seems to me, and I'm very happy, I'm looking forward to discussion afterwards, maybe, this notion seems to require in some sense an external agent, yeah? Which is not a problem, because from the beginning I said there will be external agents, you know? So there will be someone with control over N1 who can decide, okay, let me do this local operation, let me do that operation. And there will be someone in N3 who's maybe making an observation, maybe measuring something, and who can then check, okay, good. You know, in a measurement run, an ensemble of identically prepared systems, they perform experiments, they make measurement runs, and N1 decides to do something or not do something, and N3 can then decide whether the outcome depends on whether N1 did something or didn't do something, or did something differently or so. But, you know, you see it kind of, there needs to be some notion of an external agent who can decide to do something or not decide to do something, or measure something or not. Or otherwise, you know, if you think of, well, what is a local operation? You can also think of a local operation as, you know, a local perturbation of the dynamics in some sense. You could also say, well, I don't need external agents, but maybe I need something like, you know, counterfactual scenarios to be able to talk about causality. What if the dynamics in N1 was perturbed a little bit, you know? Would the content, the you know, the dynamical field content, whatever, would the observables in N3, would they feel this? You know, would the state feel this in some sense? Yeah. So there you are in this counterfactual scenario, what if? Good. But as I said, this is not a, yes, sure. Sorry.
So how is the second idea different from the first idea? Because in my intuition, maybe the first idea, you also, I mean, preparing the systems would not depend on each other. So whatever I do here will not affect this one too.
Well, yes, this is true. Let me put it like that. There is a mathematical difference in some sense. And I will get to that on the next slide, where I will talk about what I mean by a local operation.
Okay.
So the idea here in the first is really that I want to, you know, to prepare my state omega-1, and I only care how the state looks in N1. I have the state omega-2. I only care about, you know, how it looks here. And then the idea is that there should be a state. So I should somehow be able to extend these states omega-1 and omega-2 to the whole system, such that it is valid to think about this omega-1 as a restriction of a bigger state and this omega-2 as a restriction of a bigger state. But in some sense, I do not care about, you know, how this state is really extended or where this extended state comes from. So I would say that this first idea is a preparation for the second idea in some sense. But this is a good point, and I hope to answer this question in more detail now when on the next two slides, when we talk about what we actually mean by a local operation, and then and then we see possible problems actually. So I prepared this slide, which is maybe a well, for those who know, a quick reminder as always. But otherwise, maybe a gentle introduction to what we mean by a local operation, what we mean by a quantum operation. So in some sense, what operations should do is, if you think of them acting on your state space, they should map states to states. Dually, of course, you can also think of those operations as acting on the algebra. And this is, I would say, actually the more common way of thinking of operations. So you say that a map from the algebra into itself is a quantum operation if and only if it is linear, it is unital, and it is completely positive, okay? So just, you know, the idea is that operation should map states to states. So when you take a state and you compose it with this operation, this should also be a state, right? Well, clearly the composition should be linear, so E better be linear. The composition should be a state, so it should preserve the identity. So E better preserve the identity. And moreover, states are positive, right? Because probabilities are positive. So E better be positive. Now, what about this completely positive here? Actually, what you want of quantum operations is that if you have two systems, A1 and A2, and you form the tensor product, and you have two states, omega-1, omega-2, and you have two quantum operations, you know, E1 and A1, E2 and A2, you can form the tensor product. And then this composition also better be a valid state on A1 tensor A2. And for this, it turns out that you need this complete positivity. So if this epsilon is only positive, then this positivity is not preserved under taking tensor product. So that's why you need complete positivity. That this, you know, works nicely with tensor products. Now, let me give you two examples, and those are really the prime examples in some sense of quantum operations. You could imagine that you have a unit, pardon me, yes?
Hi, yeah. Hi, Max. I want to ask a question.
Yes,
so what does it mean here that the map is positive? I mean, for quantum observables, we don't really know what's larger than zero or smaller than zero.
Oh, well, in some sense, you do. Because the idea is that an element is positive if it can be written of this form, okay?
Yeah,
so
okay.
B is bigger equals 0 if and only if you can write it in this form, okay? So this holds in particular in a C-star algebra, okay? In a star algebra, you might allow here some linear combinations or so. So you have a notion of when an observable is actually positive. And you know, if you go back to this view of talking about operators on a Hilbert space, or to talk about something more familiar, right? Then if you're positive, you're self-adjoint. If you're self-adjoint, you're a spectrum. You have a spectrum. And you are positive precisely when your spectrum is contained in the non-negative real line. Yeah.
Okay. Mm-hmm.
Yeah.
So this, yeah.
Exactly. Yeah. So you do have this notion. You do have this notion of positivity there, and also in this more abstract, you know, just star algebra case, you also have this notion of positivity. Mm-hmm. And ultimately, if you think of C star algebras, it basically boils down to considerations about the spectrum of a self-adjoint operator.
Yeah. All right. Thanks.
Good. So we were talking about the example, and concretely we were talking about an observable A and a unitary U contained in A, and a quantum operation on A could be, for instance, just this unitary kick here. Okay. Or what you could also you could generalize this a bit further by having a unitary contained in the tensor product, and an operation on A1 could then be take your state on A1, tensor it together with the state on A2, then compose it with the adjoint action of this unitary on the tensor product of A1 and A2, and then, you know, evaluate this on whatever you feed omega, tensor the identity. So in a more, you know, quantum information language, maybe what this means is, you know, take your system, tensor it together with an ancilla, let it evolve unitarily, and then trace out the ancilla. Okay, this is the more abstract algebraic notion of tracing out basically some ancilla. So now, equipped with knowing what a quantum operation is, you know, we can go back to this notion of causality. And since those unitaries are really a prime example of quantum operations, we could ask the following questions. So, do local unitaries give rise to causal quantum operations? And following this, we could look at this protocol that was more or less thought of by Sorkin in the 90s. Let us take regions N1, N2, N3 as depicted here, such that N1 is spacelike separated from N3, but there might be an N2 lying in between here with intersection with the future of N1 and the past of N3. Then the protocol is N1 does something, concretely perform a local unitary kick. Okay, so this a joint action of this unitary. N2 does the same, let's say, and P3, well, we tell him to measure the observable P3. It might be a projector, so, you know, in N3, an observer checks whether the detector clicks or not. Good, so we start with the state omega. If N1 performs the unitary kick, we get this, you know, U1 dagger U1. Now N2 performs the unitary kick, so we get the U2 dagger U2. And in N3, the observer measures. So if we evaluate this on the state, the observable P3, and in particular causality holds. So N3, the outcome of N3 does not depend on whether or what N1 did if this U1 dropped out. And now it's really in some sense easy to see that there is no reason for U1 to drop out. Because, I mean, P3 commutes with U1, but U1 does not commute with U2, and U2 does not commute with P3. Because, right, N1 and N2 are not spacelike separated, N2 and N3 are not spacelike separated. So we really cannot expect this equality to hold in general. But that means that if we define our, you know, our causality, this notion of causality as if you do something in N1, N3 doesn't know, no matter what happens, then, well, there is a problem. And there are two options. So either you say that P3 is unobservable, or you might say that unitary kicks are impossible operations. So what do? You need to do something in order to have this notion of causality maintained. You either need to restrict the observable content of your theory, or you need to restrict the you know, conceivable, mathematically possible quantum operations to maybe more physical quantum operations, to causal quantum operations. And this is precisely what I want to do. So I want to take the approach that all observables should be observable. So in particular, I want to look for causal operations. And here is the note that trivial action at spacelike separation is necessary, but not sufficient. Okay? Because this is precisely what we saw here, right? So because of spacelike commutativity, the operation that maps omega to omega of u dagger u1, right? This acts trivially anywhere spacelike separated from n1 because of spacelike commutativity. But this is not enough, yeah? Which is precisely the point. So without further ado, let me get to the main result, which is the following, okay? So local perturbations of the dynamics yield local scattering maps and causal operations, okay? So I appreciate this is maybe a bit vaguely stated, but what it means is the following. Suppose you're in a scenario as before, N1, N2, N3, okay? And now we want to perturb the local dynamics in N1 in such a way that we get a local scattering map, and the same in N2, okay? So we have some local scattering maps, θ1, θ2. They act on the algebra, right? They are scattering maps. And now we could ask the same question, okay? So omega first, then the guy in N1, you know, the system scatters because N1 perturbs the dynamics a little bit, couples a probe to it or whatever, couples an ancilla. So this is followed by θ1, N2 does the same. So we have θ2. And then we evaluate this again on P3, which lives inside here, okay? And now this is a fact. This is a nice fact about local scattering maps, about perturbations of the dynamics. A nice thing is that this θ2 applied to P3 can actually be localized in this region L here, okay? So the observable in some sense, θ2 applied to P3, okay? This observable can be thought of as living in here, okay? It can be localized in there. But what we see is that this guy here, this L, is spacelike separated from N1. And the scattering in N1 should act trivially on something that happens at a spacelike separation. So in particular, the θ1 drops out and the equality holds, okay? There is no superluminal signaling if your operations are coming from local perturbations of the dynamics. This is in some sense the gist here. So you might say, oh, okay, but this looks a bit weird, right? Why is it exactly the case that this θ2 applied to P3 can be localized in this region here? Where does this come from? Well, there is a more abstract proof about the properties of these local scattering maps, but you can actually also get some intuition about this more explicitly in something like Lagrangian perturbation theory. So in Lagrangian perturbation theory, you have some unitary S matrices, which are given by some time-ordered exponential of some integral against some Lagrangian interaction density. And because we want to talk about local scattering here, we say that we only care about, you know, Lagrangian densities that are supported inside, well, N1 and N2. Okay, so we only integrate over N1 and N2, and we ensure this by maybe multiplying your Lagrangian interaction density with some cutoff function, space-time cutoff function. Yeah, and then these scattering operators theta act as a joint action by these unitary S matrices. And then precisely because this guy here is a time-ordered exponential, when you actually look at the expression θ2 of P3, you actually see that you can indeed localize this thing in a region that is spacelike separated from N2. Okay, so if you're more interested in that and see this more explicitly, maybe we can discuss this in the following discussion session. But at this point, this is everything I wanted to tell you in this direction. So yes, we have a nice set of quantum operations that are causal. The next thing is, okay, now what? What can we do with that? And those are the last two slides. So I want to use the last few minutes that I have to talk about an application, which are causal measurements. Okay, so there is this approach to measurement where you want to use a probe to learn something about the system. Yeah, you could say this is a very operational approach because this also is what happens in the lab when you take a detector, you couple it to the system, you look at the detector. So you use a probe to learn something about the system. So abstractly speaking, the setting is you have a system S, you have a probe theory P1 in an initial state, and you might have a coupling between S and P1, some local coupling, which gives rise to some scattering operator θ1, let's say, okay? And now let me skip the rules of the game for a second. We can now ask the question, what is the expected outcome of the observer's measurement of probe observable P1 in P1, okay, in the probe theory? So let's say the observer looks or observes some projector in the probe, on the probe side, whether the detector clicks or not. What's actually happening is that the whole system is, right, the combination, the tensor product. You have the system in an initial state omega. There is the probe in an initial state sigma 1. You have to appreciate the interaction between the two via this scattering operator here. And then, well, the observable that the experimenter looks at is the identity on the system side and P1 on the probe side. So this is indeed what the observer measures, okay? And it turns out that this is precisely given as omega of this quantity here. And this quantity here lives in the system, so it's a system observable, and it is unique, and it is called the induced system observable, okay? So in other words, if in this coupled system, the observer looks at his probe at P1, what he gets, the value that he gets is the same as the expectation value of this induced system observable in the initial system state. So this here really is the core element of the statement. When you look at the probe, you can learn something about the system. So, and now in my last 2 minutes, let us talk about multiple measurements and causality quickly here, okay? And in order to talk about that, we need to talk about more measurements than just one, okay? So as before, we have a system, but now we have n observers, let's say, with each their own probe, which we could combine to a super probe, let's say, in initial states sigma, and we have super initial state, just the tensor product of the sigmas. They each couple their probe to the system, gives rise to scattering operator θj. And then we have a super scattering operator θ. And we assume everything to be in causal order, okay? So we assume that, the first observer might do something in here, the second observer might do something here, right? So there's a nice causal order and so on and so forth until the nth observer does something here, okay? Nice in causal order. So now, let me get to the rules of the game. As you see, in some sense, we say that every observer gets one probe, which is precisely what I said, or rather one probe theory per measurement. So what I'm really describing here is in some sense, and one measurement run, but because the outcome is probabilistic, you have to think of those as really ensembles of individual measurement runs, okay? An important point is that the probes themselves are not updated. Nothing happens to the probes, even when you have multiple measurements, okay? So let us ask the same question. What is now the expected outcome of jth observers, of the jth observers measurement of the probe observable Pj in the probe theory Pj. Well, as before, right, we have the system state, initial system state, the initial super probe state. Then we have this super sketching operator that encodes the coupling of all the theories. And then we have identities everywhere apart from the jth slot where we have Pj.
Max, let me interrupt you to give you a 5-minute warning for the timing of the time.
Oh, that's great. Okay. Thank you very much. Good. So then this guy here is in the jth slot. Okay. Now you can just expand because, right, so this sigma and this theta were defined above here. You can just expand this. And what an easy calculation shows is that everything that happens after J with respect to this causal order that we had here drops out. Okay, this follows immediately, okay, that there is nothing to discuss, which is nice because in some sense this immediately gives you that there is no retro causality, no influence from the future to the past. Nothing that's in this causal order ordered after your J can signal back to J, okay? This is great. And now moreover, if we have this expression, you can easily rewrite this in terms of, again, you know, an induced system observable, and this is really jth induced system observable, and an updated state omega prime, where the updated state omega prime is given by this expression here, okay? So before we go into the details here, let us quickly appreciate this formula. So if the jth guy measures or observes the probe observable Pj, what he measures, the outcome, is the same as that of the system observable induced by his observable, his coupling, and his initial probe state, evaluated in not necessarily the initial state, but an updated state. So he again learned something about the system, but of course, you know, the system state changed because before him, there were J-1 other agents who performed a measurement, okay? And now let us get to this updated state. This omega prime is precisely given by this expression here. And what we notice is that this only depends on how those J-1 agents measured and not what they measured, okay? You might say this is trivial because, well, this is precisely the question that we ask. We ask what is the expected outcome of jth observer's measurement. We did not condition this on any outcome, right? So there should not be a selective update, okay? We should not select on, oh, okay, the sub-ensemble of all the measurement runs where the first observer measured spin up or something like that, okay? This is not the question that we asked. We ask what is jth observer's outcome, and indeed, we get this updated state here, okay? In that sense, updated states are emergent if you think of measurements described by coupling probes to a system in this context. Now, of course, the other interesting bit is now this updated state, okay? This omega j, when you evaluate it on this system observable, this induced system observable, does it respect causality or not? So what is one of those observers, the ith observer, which is, you know, smaller or equal J-1? What is if this guy was space-like separated, let's say, from J, from Nj, from the localization, the region of control of the jth observer? And then it follows from what we discussed before that, you know, the updated state is given in terms of sketching maps, local sketching maps, local dynamics. It is an easy generalization once you go through the math of what we discussed before, that indeed, if you have some observer I that is space-like separated from observer J, then the sketching operator of I drops out of this equation here, okay? So you could just discard him. You could ignore him as if it never happened, as if this person did not measure at all, which is precisely what we want. No matter whether this person measured or not, no matter how this person measured, it drops out of the equation in the end. So this is really a causal description of measurements.
Please conclude, Max.
I'm on it. Thank you very much, Jose. In summary, the two sentences here: local scattering maps yield causal quantum operations, and local measurement between probes and system give induced system observable and state updates. And now a little outlook. You might ask the question, okay, good, but this sounds like an interesting maybe procedure to measure system observables, those induced observables, but what observables actually can you measure? And let me tell you that this is currently a work in progress together with my supervisor, Chris Fewster, and our collaborator, Ian Jubb from Dublin. And I thought about turning it maybe into a teaser. So if you're interested in this, watch this space, there are interesting results coming up. And with this, I would like to thank you for your attention.
Okay, thank you very much. Yeah, okay.